Hello, math humans. We're going to do 2.6a today. We're going to be talking about related rates. Our objectives are that we're going to use implicit differentiation to find the rate of change of two or more related variables that are changing with respect to time. So here's the classic example. When water is drained out of a conical tank, the volume V and the radius R and the height of the water level are all functions of time. And so here is the volume of a cone, right? So I have a conical tank. So here's my cute little tank, right? Here is its radius. Here is the height, okay? And then the volume is that particular formula. Water is coming out of my little tank. And so if I want to find, let's say I want to find the rate of change of the volume. Okay, so that means that I would take the derivative of this equation. So I'm going to rewrite it as volume is equal to pi over 3 r squared h. Well, this is a classic implicit differentiation problem because in theory, if I took the derivative of all of those variables, I would get a dv dt because I'm taking the derivative with respect to time. And then I would do some math and I would get a dr dt and I would get a dh dt. And so, oh no, that's a lot of things to solve for. So in a problem like a related rate, what we would do is we would solve for one of these rates and we would have other equations that help us to minimize the number of variables. Typically, not always, but typically, we're only going to manage two variables so that I only have two different rates. Maybe they give me the third rate, but that also means that I have to have two related, hence related rates, equations. Okay? All right, so let's just jump right in and talk about a problem. Okay? So we're going to do our first example. Do it in purple today. So first example, I'm going to have a pebble is dropped into a calm pond, not a rowdy pond, but a calm pond, and it's going to cause ripples in the form of concentric circles. Because life is all about math and physics, R-C-E, and spelling. And remember that concentric circles mean they have the same center and then they look kind of like that. The radius, R, of the outer ripple is increasing, which means positive, by the way, at a constant rate and of 1 foot per second when the radius is 4 feet at what rate, so many T's, is the total area of A, I guess there's no of in there, A of the undisturbed water changing. Gotta love math symbols. Okay? So when we do a pebble, bad spelling, when we do related rate problems, the first thing that you need to do is write down everything that's given, write down what you're looking for, and draw a picture. So my first thing I'm going to do is draw a picture. Here's my cute little first part of my concentric circle. and I'm talking about area, I know that the area of a circle is pi r squared. So we're told that the radius is increasing at a constant rate. So dr, the radius with respect to time, is going to be changing at 1 foot per second. And it says at what rate is the area changing? So I want to find dA dt when the radius is equal to 4 feet. It is really, really important that you take the time to do this, because this is going to help you know what you're looking for and what I can substitute in. The good thing on this one is when I take the derivative, I only have two variables, so I don't have to have a secondary equation. So I'm going to rewrite this right here. Remember, pi is a constant, and I'm going to take the derivative. dA over dt is equal to pi times 2r dr dt. So related rate problems are done very similar to implicit differentiation, because really that's what it is. And every time I take the derivative, it's going to generate a dA dt, a dr dt, a dv dt, a d whatever dt. And then I either am going to have values to substitute in or things that I can solve for. So I'm going to rewrite this equation as 2 pi r dr dt. We're looking for dA dt, and we know dr, and we know the radius. So now I'm going to write that dA dt, and I'm going to find when r is equal to 4 feet, is going to be, here's the 2 pi, the radius is 4, and dr dt is 1. We'll talk about the units in just a second. So this is going to be 8 pi. And just like we talked about several videos ago about knowing what the units are, this tells me right here exactly what my units are going to be. Area is feet squared. Time, in this particular case, we're changing in seconds. So you never have to worry about how to find the units, because it tells you exactly what the unit should be. Alrighty? So then I would write dA dt evaluated when r is 4 feet is 8 pi feet squared per second, and that is a rate. A rate is a derivative, and it means that I get to do some fun math. Alright, let me do another example for you. I like related rates. They can sometimes be so challenging, but occasionally they're really pretty fun. So here's our second example. Air is being pumped into a spherical, yay geometry, balloon. I think I spelled that wrong. Maybe not. At a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. All right. So again, I'm going to start by drawing a picture. Here's my cool picture. Here's my little balloon. Whoop, whoop, whoop. Here's a string. I know that it says air is being pumped into, so that means this is positive, and it means that it's a rate, so it's a volume, cubic feet per minute, dV dt is equal to 4.5 cubic feet per minute. The volume equation for a sphere is V is equal to 4/3 pi r cubed. Again, that's one of those formulas that you're just expected to know. And I want to know what is dr dt is when my radius is 2 feet. This, again, this process is super important, because as the problems become more complicated, you will have more equations to write. So I only have two variables again. In the next video, you'll have more. But in this video, I still only have two variables. So I go, yay, and do my happy dance. So when I take my derivative, dv dt, implicit differentiation, is equal to 4 pi over 3 times 3r squared dr dt. Okay? So I'm solving for dr dt. So, and I know this, and I know this, so I'm going to clean up my equations, so my 3's cancel. So I have 4 pi r squared dr dt. I'm solving for dr dt, so dr over dt is going to equal dv over dt divided by 4 pi r squared. Well, I know dv dt is 4.5, and then I have a 4 pi, my r is 2 squared, and so when I do this math, I get 4.5 divided by 16 pi, and this is going to be 0.09, and let's talk about our units. A radius is measured in feet, and time in this case is going to be measured in minutes. And that was given back in the problem, so I'm going to maintain consistent time. Changing would mean I have to do some dimensional analysis, and then I'm done. So my dr over dt, when r is equal to 2 feet, is equal to 0.09 feet per minute. I could also have left it as a 4.5 over 16 pi, and that would have been sufficient. Important thing to notice. When you sit for your AP exam, the rate is different at every different set of criteria, and oftentimes in an FRQ, you will get 1 out of 9 points just for having the correct units. Units are important, always, always, always. Remember that your cool rate tells you exactly what the units should be. Radius is linear. There's my linear unit of measure. Time is going to be always given in the problem. All right, my dears, that is it for today. I will see you soon.